In this class, we're going to take a look at the chain rule for integration. So this works in reverse of the chain rule for differentiation. It's actually sometimes called the reverse chain rule. So you'll remember that for differentiation, the chain rule applies to composite functions. So same here with integration. This is a rule that we use for not for polynomials like the power rule, but for composite functions. So a composite function, remember, is some function h of x, which is made up from the composite, so sticking together basically two functions, say f and g, something like that. But in reality, that's not what the functions look like when we come to differentiate or integrate them. Normally, with this question type, you see a composite function in this form. So some polynomial inside a bracket with a power on the outside. So just to fire up an example from differentiation, so let's say we had something like 2x minus 5 to the power of 3. So this is one function. This would be like your g of x, so that's a polynomial. The overall bracket with the power is an exponential function. That would be like your f function. So that's why this would be a composite. This is a common scenario that we're dealing with when we're talking about the chain rule for both differentiation and integration. Although the truth is it could be presented in other ways. There's different forms of composite functions, so don't think it's only these, but this is the most common form. Another example would be something like, say, a sine or a cosine with a power here. So maybe sine 4x, so sine x to the power of 4. So that is, if I rewrite it, basically just sine x in a bracket to the power of 4. So again, you've got like a function in here, which this time is a trig function, and then you've got an overall exponential function. As a reminder, this guy here, for differentiation, would differentiate by multiplying by the power. So we're kind of starting by using the power rule. And in fact, the chain rule for differentiation is really just using the power rule twice. So we do the power rule there, so I've multiplied by the power, reduced the power by 1, and then we just times by the derivative of the inside. So we're using the power rule on the inside to get 2. So the derivative of 2x minus 5 is 2. Merging these guys together to give us a 6 bracket 2x minus 5 to the power of 2. So that's how we did differentiation for chain rule. When we come to integration, we're going to have to reverse that process. So like the power rule for integration, we're going to increase the power by 1, divide by the new power. The thing that makes it a little tricky though, this rule, even though it's an integral, involves a derivative. And it's maybe a little difficult to explain, but I'll try and show it with this one why that's the case. Difficult to explain in theory, but it's basically because remember that if we integrate this, we should go back to the derivative. So the result that we get here, in fact, to flip that, the result that we get here, if we differentiate it, it should take us back to the starting point because derivatives and integrals are opposite. It's partly, well, it's entirely actually to do with that reason. That's why this is going to end up having a derivative in it. The fact that this chain rule has got a derivative as part of the process means that the integral equivalent needs to have a derivative as part of the process. That can be a little confusing at first, but you'll see by example that when you actually come to work these, it doesn't really cause that many problems. So we're just going to start by reversing the chain rule, which means that we're going to increase the power by 1. Just like normal power rule integration, we're going to divide by that new power. So I'm just going to write that over 5. The thing that then makes it the chain rule is that we also divide by the derivative of the inside of the bracket. So the derivative of 2x plus 3 is by the power rule 2. We could write that as like over 2 to create a second fraction, but that starts to get ugly. So we don't need to do that though. We can just put the 2 on the bottom of the fraction that we've already got by timesing it to the 5, multiplying it to the 5. And that's because we wanted to divide by the 2. We could write divided by 2, but a smarter way to do it, a neater way, is just to put it on the bottom of the fraction. If it's on the denominator of the fraction, it's already dividing, so that's the neatest way to do it. And then of course we need to put a plus c on the end. So then we would just maybe tidy that up by timesing these guys together. So 2x plus 3 to the power of 5, either over 10 or 1/10, either way, whichever way you want to do it, like this. And there we are. So the reason why we use a derivative is because if you imagine at this point here differentiating this, if we differentiated this, we would multiply by the power. So that would, let's multiply by the power to bring a 5 in front. This is differentiating. We would then reduce the power by 1, so it goes down to 4, and we would then multiply by the derivative of the inside of the bracket. This is for differentiation, so multiply by 2. And notice what would happen there. That guy would cancel with that guy would cancel with that guy, and then we end up basically back where we started, which is what we would expect, because we took our integral, we differentiated there in red pen, and that should take us back to where we started. So it's the fact that we need to cancel out the 2 here that requires us to divide by the derivative, because in the chain rule for differentiation, this derivative of the inside is going to go here. In the integral, we need to kind of cancel that out if we're going to end up getting back to where we started. So that's why we put the derivative on the bottom of the fraction. That's kind of more than you need to know in a way. In terms of actually using these rules, you'll never need to think about that. You can ignore the red pen, basically. You just need to work through the mechanics and just know that they have to be opposites of each other, differentiation and integration. Okay, right, so putting all that horribleness to one side, let's just focus on the example here. So increasing the power by 1, that's going to take it up to a -4, dividing by the new power, -4, and timesing that to the derivative of the inside, which is 3, plus c, and then usually we can take a line to tidy that up, so it's -12. Just for a bit of variety, I'm going to write it as -1/12 and put it in front of the bracket. There are times when that might be more convenient. There are times when it's better to write it in this form. You've got a negative power here on the bracket. You could turn that into a positive power by writing it as a overall fraction. So I could maybe write this as -1/12 and then just bringing this guy down to the bottom and putting a positive power. And remembering your plus c's all the way down. Real easy to forget about the plus c. So yeah, different forms there. They're both valid solutions. Okay, turning our attention to this guy, just do the same thing again. So increase the power by 1, that goes up to a 3. Divide by the new power, so over 3. This time the derivative is -7 because the terms are the other way around. So the x term was first here. This time it's second. That's because it's got a negative. Putting the plus c on the end, and then just taking a line again to tidy that up. So they're not too bad, these, once you get into them. They're a little confusing at first, but you'll learn to just flow through them fairly quickly. You can always test it by saying, hey, if I differentiated this, where would that take me? So just to differentiate that again, so multiply by the power, which would be bringing the 3 there, reducing the power by 1, then multiplying by the derivative of the inside. The derivative is -7. 3 times -7 is -21, so that would cancel that -21 with this guy, and we've ended up with 5 minus 7x to the power of 2, which is where we started. So that's just a way you can test your integral by taking what you get, running it through the derivative, so y dash or dy dx. I'll maybe write that as dy dx. Basically, you can test it by taking your answer, differentiating it, and seeing if you get back to where you started. Okay, and the final example, this guy's not quite in an integratable form because it's got the variable kind of term on the bottom of this fraction. So we're just going to take a line, first of all, here to fix that. So we're going to keep our integral sign because we're not integrating yet. We're just bringing that bracket to the top and making it a -3 power, like that, just using one of your indices rules. And then we just proceed to use the chain rule, or the reverse chain rule. So we increase the power by 1, divide by the new power, -2, times the derivative of this, which is just 1 in this case, put our plus c on the end, and times in anything by 1 doesn't really change it, so that's just going to end up being a -2 on the bottom. Again, you could change this to make it a positive power just by bringing that to the bottom of your fraction, so you would end up with -2. Let me just tidy that up a little. So you would end up with -2 on the denominator times to the bracket x minus 3 and make it a +2 power. So that's a reverse chain rule. So basically the chain rule for integration. Definitely a little confusing at first. Don't expect to find it like super easy. You will be confused by the fact that you're always dividing by the derivative. Everyone tends to get a little confused by that at first, but after working a few examples, the process never really changes all that much. And just anytime you're doing integration, kind of testing, at least in your head, testing your answer by differentiating to see if you go back to where you started. So definitely worth checking out a few practice questions, I think, on this topic, just to get that technique down.